Hey everyone, and welcome to the final video on my series on physics-informed neural networks. In this video, I will be teaching you how to implement the training function and the main execution of the program. So we can start the training function by defining a method known as the PINN underscore train. Here we pass the parameters which is z, xi, x naught, v naught, and the number of epochs that the model is going to go through. So here we're going to initialize our number of epochs as 5000, and we're going to put this model on the CPU device. So here we're going to explicitly define the model variable. So we're going to put model is equal to PINN, and we're going to put this on the CPU device, so we can do to device, and we can use the optimizer is equal to optim. Here we're going to use the Atom optimizer. You can use any other optimizer according to your choice, like stochastic gradient descent as an example, but for this series I'm going to use the Atom optimizer. Here what model.parameters do is that it takes in the weights and biases of the layer we defined previously and adjusts them according to the learning rate. So what LR basically stands for is learning rate, and it learns at the rate of 0.001 steps. So we can now define the time taken for the program to execute. So we can write tech is equal to time dot time. So now we can define the loop to print the number of epochs and the loss functions after each iteration. So we can write for epoch in range epochs. So it's usually good practice to call the model dot train function in the beginning. After we call model dot train, we define the loss equation, which is the PD residual function that we previously defined in the last video. Residual equals model. So here is the residual of the PDE. Here is the initial condition boundary loss. So now since we have the PD residual and the boundary condition loss, we can define the overall loss function as loss is equal to loss underscore equation plus loss of the initial condition. Now here we do the optimizer dot zero grad. What this does is it resets the gradient to 0 after each iteration. Now we do the loss dot backwards for the backward propagation. What this function does is that it adjusts the weights and biases according to the loss functions. Now after we do the backward propagation, we can initialize the optimizer step. I got the spelling wrong. Optimizer step. Now we print what the loss is after like around 500 iterations, because we don't want the terminal to print all 6000 iterations or 5000 iterations. So we can write if epoch modulus, let's say after every 500 we want the terminal to print, we can print, we put an F string there, epoch comma the loss, and the loss dot item. And here we're going to use scientific notation, so we can write dot 6e. So now we can print the elapsed time, so we can write print elapsed time is equal to we can write the time that we defined previously, time minus tick, and we can write seconds over here, and we can return the value of the model, so we write return model. So this is how the training function is written. Now it's time for the code for the main execution of the program. So we can start off by writing if name is equal to main, the number of points, so number of points is equal to 500. Z will be the line space, so Z is equal to, here we call the numpy library, so np dot line space 0, 20, npt, and now we reshape this into, we reshape -1, 1. Now here we write the damping ratio, so the xi value, so we write xi values is equal to np dot random dot uniform. So we write this because we want it between the 0.1 and 0.4 range, so we can write 0.1 0.4 range, and we can write the size, so the size is equal to the number of points 1. So this creates the array. So we'll take the initial conditions, so we have defined x0 and v0 in all the parameters, but we never explicitly gave it a value. So in the problem statement, x0 was given as 0.7 and v0 was given as 1.2, if I remember right. So we can write device is equal to, here we check whether the device can use the CUDA architecture, CUDA, if torch is available, or else CPU. Now here this is the model, which is a PINN train, all the parameters pass through it, and we close it. Now we have the xi underscore eval will equal to 0.2 into np dot ones like z. The z tensor will equal to torch dot tensor z comma d type is torch. We have the xi tensor, so yes, everything seems correct here. So now we get the input eval, so this is what is going to enter the model. We have defined the z tensor and the xi tensor, so input underscore eval is equal to, so we concat the z tensor and the xi tensor, so tensor operations can occur in these two, is equal to torch dot concat the two tensors with a dimension of 1, And now we can call this, we call this x predictions more than evaluate. We call this x underscore predictions is model evaluate. Here we can detach dot cpu dot numpy. So here we're going to now define the analytical solution so it can be compared to the actual PINN predictions. So here it's going to be, we're going to define the damped oscillator z comma, so we can write x naught here. We'll just define the value as 0.7. We can define v naught as 1.2, and the xi tensor, which is the damping value, equal to 0.2. So here we have defined the damping functions. So we write omega underscore d is equal to np square root 1 minus xi into 2. So now we can return np dot exponential of the negative xi into z, where's the into z, whole thing into the x naught into, is it, yes, it's np dot the cosine of omega underscore d into z into z plus xi into x naught divided by omega underscore d multiplied by np dot sine, okay, this is a pretty long one, but I've defined this in my previous video. So omega into, omega underscore d into z. Okay, I'm hoping that this part is correct because it was a pretty long one. I've given the derivation in my second video on how to derive this particular formula for those confused. So now we're at the last stretch of this series. Here we just need to visualize our data. So here we can plot our figure, fig size. We'll keep it at 8,5 for now. So we'll keep it 8,5. Plot x predicted. So I will just copy paste the code from one of my reference codes I have on the side, which is basically the matplotlib code. Now the last thing to do is just to run the model. So we can run the model here and wait for the execution. This will take approximately like a minute for the model to calculate everything. So we shall see the results after a minute. So after about 52 seconds, we can see our prediction of how the PINN predicted versus the actual analytical solution. So before I end this series, uh, I would like to apologize because here we were supposed to define Z0 and Xi0 for the initial conditions by explicitly defining them here. So other than that, we can see how well physics informed neural networks can be for predicting the values for a damped oscillator. If you guys enjoyed this series, I would appreciate any feedback in the comments. So thank you for watching.